Hello. So yesterday we had seen something about central orbits and central forces. We had seen the above relations when we are using pedal equations and how the perpendicular distance p relates with r and theta. Okay, so that is given by the above equation. And also we had seen that when we are using polar coordinates and pedal equations, we had we have the following equations given below. So that is what we did yesterday. Today we will learn something about sectorial area, and then we will learn something about areal velocity, and also a very important theorem which states that the areal velocity is always constant. All right, so let us just go ahead with it. But first, let us just understand what sectorial area is. Okay, so now over here we are having that the particle is traveling this black path. Okay, so just let me draw it again. Okay, I will keep this picture, but for you to understand what areal velocity is, first of all, you will need to understand sectorial area. So suppose the particle is traveling, okay, in this path. Now, what do you mean by sectorial area? What do you mean by sectorial area? Just think of 2 points, P and Q. Okay, and this one, it is the pole. Then the area of OPQ, then the area OPQ, it is called as the sectorial area. Okay, firstly the particle was at P and then it was at Q. Then this area OPQ, it is known as the sectorial area. Okay, so let me just describe it. Let a particle moves from P r1 theta 1 to Q r2 theta 2. Then the sectorial area is the area OPQ. Okay, take note that it is not a triangle. Okay, because P may be somewhere here and Q may be somewhere over here. R1 theta 1, R2 theta 2. It is not a triangle. Make sure that you understand that it's not a triangle, because even though these are straight lines, it is clear that this one may not be straight. Okay, but when we are dealing with areal velocity, you will see that PQ will behave as a straight line. Why exactly? You will see. Areal velocity will therefore be defined like this. The rate of description of the instantaneous description of the sectorial area. So what is happening over here? Remember that when we are dealing with velocity, we have to use limits. Okay, just like in limit t tends to 0, dx dt will give you the velocity in the x direction. But over here we are dealing with the rate of description of the area. So what is happening? Firstly, the particle was at P. Next, the particle is at Q. Okay, remember that we were having this limit t tends to 0. Okay, so similarly over here, what we will be doing, since we are dealing with areal velocity, we will be having something similar like this. Okay, t tends to 0. And over here, P and Q. Okay, particle moves from P to Q. But since the time, we are taking such a very small time interval, That is why P and Q, they are very, very close to each other. Even though in the picture it's showing that they are quite far, okay, but just know that they are very, very close. So if they are very, very close, what happens is PQ, even though it is a curve, okay, but because P and Q are very, very close, so PQ behaves as a straight line. And because PQ behaves as a straight line, therefore the sectorial area over a very brief amount of time, it will be the area of the triangle OPQ. Okay, so let's see. Okay, let a particle moves from P r theta to a new position Q. Because it has moved to a new position, so also the radius vector will change. Okay, it's no longer r, it will change by some amount delta r. Okay, we can easily write this one maybe as r plus h, but it is best that if we are using delta r, okay, just to keep the notation a bit simpler. Okay, otherwise we will be confused. What is h? Also, we have already used something for h. Maybe if we use other letters also will be confusing, so that's why we are using delta r. So that is why, since the radius vector will now change, it has changed by an amount delta r. Similarly, theta, okay, it has changed from P to Q. So if this is for P, then for Q will be theta plus delta theta. So I hope that is clear. Okay, over a brief amount of time, del t. Okay, so after time del t, it has moved from P to Q. Okay, since we are concerned with areal velocity, we will take limit del t tends to 0 if the time is very, very small. Okay, so therefore areal velocity, it will be equal to limit del t tends to 0 sectorial area POQ divided by del t. So this is the rate of description of the sectorial area, okay, which we shall call as the sectorial, which we shall call as the areal velocity. So we will keep this one as it is. But again, since now the sectorial area, it behaves as a triangle POQ. It behaves as a triangle, so that's why we will say area triangle POQ by del t. Okay, some of you may not remember what the area of triangle POQ is. Okay, but just know that we can even use vectors over here. So if you remember, it will be OP vector, the magnitude OP vector cross OQ vector divided by del t. So limit del t tends to 0. Okay, I will keep 1 by 2 del t, and OP cross OQ, it will be magnitude OP, magnitude OQ, sine the angle between OP and OQ, the angle between OP and OQ, which is del theta. And also we will be having that unit vector, but once you take the magnitude, it will be equal to 1. So this is how we will do it. So we are achieving this line. Next, what we will do, OP the magnitude, it is r, and 1 by 2 I can even take it outside. So limit del t tends to 0, OP will be r, and over here OQ will be r plus del r, and sine del theta by del t. Next, what I will do some modifications. Okay, sine del theta, I will divide it by del theta and then multiply it, and also I will keep del t. Okay, so this keeps the equation. Okay, but it just changes it a bit. Okay, in fact it doesn't change the whole thing. Okay, it's just that we are introducing new terms. Okay, so sine del theta by del theta, it will be equal to 1. If you remember limit x tends to 0, sine x by x will be equal to 1. Okay, but over here we are having del theta. So what I can write, okay, this one will be equal to 1. And over here I will be having del theta del t, which I will keep it. And the reason for this, I can write it as, since if del t it's very, very small, if time is very, very small, then this theta will also be very, very small because q is very close to p. Okay, since del t tends to 0, it implies that del theta tends to 0, and therefore sine del theta, which is equal to 1. Okay, so that is what we are having. And also keep note, if the time is very, very small, okay, p is very close to q, then del r will also tends to 0. So what you are having, del r will tend to 0, so you will be having only r squared del theta del t, which is theta dot. Okay, when time tends to 0. Okay, again I can write it over here, since del r tends to 0 if del t tends to 0. Okay, so I hope that is clear. So we are having that this one is equal to half r squared theta dot. If you take a look at the equation below, r squared theta dot, okay, in fact I can write this one as theta dot by 2u squared. So theta dot by 2u squared, if you notice, it will be equal to h by 2. Okay, by using the fourth equation. Okay, since theta dot equal h u squared. Okay, so what does this say about the areal velocity? This says that the areal velocity is constant because h, it is a constant we have learned in the previous class. Okay, so this says that areal velocity is constant. Which gives that areal velocity is constant. Now, what are we going to do? So we have proved that it is constant, but also what we will do next is we will show that the areal velocity, it's also related with p. Okay, it's also related with p. Relation. Okay. Okay, I will frame this one as a question. Prove that. Okay, the areal velocity, it's equal to half vp. And number 2, v equal h by p. And number 3, v square equal h square okay, excuse me. Okay, so this is what we really want to prove. Okay, this gives us another relation for the areal velocity. Okay, and then we will be having v, which is the velocity. Okay, take note that v, it is not the areal velocity but just the velocity of the particle, and the velocity of the particle, it always acts tangentially. Okay, and also this is a relation between the velocity, okay, and du theta and h. Okay, so this is what we will do. And also for the last equation, when we were having that areal velocity equal h by 2, okay, we will name that one as equation 1. Okay, so now let us proceed. Again, okay, solution. Okay, even though I'm writing it as a first line, okay, but since it is also a continuation of what we had done, okay, so that's why I'm writing again areal velocity. It's equal to limit del t tends to 0. Okay, area triangle POQ, again for the very same reason that now it behaves as a triangle if P and Q are very close to each other by del t. So we had last time, okay, just before this, we had calculated the area of triangle by using the cross product. But also we can use that very simple formula that area of triangle is equal to half into base into altitude. Okay, keep note that P and Q are very close to each other, so you will be having some kind of a straight line like this. Okay, POQ. And now what is happening? Okay, and the altitude of this triangle, it is nothing but P. Okay, the base, it is PQ, and the altitude, it is P. Okay, so this is what we will be getting. Del t tends to 0, half into base, which is PQ, into P. Okay, by del t. Okay, since the perpendicular, it is ON. Okay, so this is what we will be getting. Okay, now PQ by del t. Okay, P, it is also constant. Okay, P, it is also a constant for this one. So that's why we can write it as okay. So limit, it will be equal to half P. Limit del t tends to 0. PQ by del t. Okay, so PQ by del t, PQ by del t, let us examine that. PQ by del t. Okay, so if Q and P are very, very close to each other, then PQ will behave as a tangent. Okay, so since it behaves as a tangent, so this one will behave as the tangential velocity, which we can write it as V. Okay, so I hope that is clear. Okay, so this is how we can do it. Okay, so it will be equal to half VP. Okay, so I hope that is clear. So we have derived another relation for areal velocity, which is VP by T. Okay, so to get the next relation that we want from 1 and 2, okay, so from 1 and 2, we will be getting h by 2 equal Vp by 2. Therefore, h equal Vp or V equal h by P. Okay, to get the next relation 3, okay, which is equation 2 that we want to find. Okay, the next relation, we will just be substituting everything over there in the equation above. Also, we have 1 by p square equal 1 by r square plus 1 by r4 dr d theta whole thing square. Okay, but now h is equal to vp. Okay, so instead of p I can write h by v. Okay, v square by h square. Okay, and 1 by r square, if you use equation 4, it will be u square plus u4. And what about dr d theta whole thing square will be d theta of 1 by u whole thing square. It will be equal to minus 1 by u square du d theta whole thing square. So that's why we will be getting du d theta whole thing square and 1 by u4, which gives us the last equation that we want to find for today, which is u square plus du d theta whole thing square. And then we can conclude, therefore v square equal h square u square plus du d theta whole thing square. Okay, so all these relations that we have found today, they are also very important. Until next time.